Chapter 3 is all about chemical reactions and balancing them, which involves stoichiometry. And I do realize that that might be a newer concept for you all this year. So, in a chemical reactions, like we saw in Dalton's atomic theory, we're not changing one element to another, we are actually just rearranging the atoms, or technically also transferring electrons. For the sake of our class, we're going to think about it as a rearrangement of the atoms most of the time. So here we have how we write our chemical reactions. We have our reactants on the left, an arrow. So these are the things we start with. So these are starting points. And we write an arrow indicating that a change has occurred. We often say our reactants yield our products. Our products are what we are finishing with. And so what we start with, in this case, hydrogen molecules, H2, and an oxygen molecule come together to make water, H2O. And we don't just have one hydrogen molecule and one oxygen making one water. We need because we have the law of conservation of mass, we need the amount of atoms of what we start with to be what we end with. So in order to do that, we need 2 hydrogen molecules with our 4 atoms here, give us 4 atoms on the other side on our water. 2 atoms from our oxygen molecule break apart into the oxygen atoms on water. So when we balance our reactions, we want to generally start with an element that shows up only as one reactant and product, ideally. So if we look at this reaction here, we have methane, CH4, and oxygen, O2, yielding carbon dioxide and water. We can see here, though, carbon shows up only one time in our reactant and one time in our product. Similarly, hydrogen shows up one time in our reactant and one time in our product. So both of those would be fine to start with. But oxygen shows up as a reactant one time, but twice as a product here and here. So we would not want to start with oxygen to balance. When you balance, you change the coefficient in front. This is the number of how many of those molecules or atoms there are. So in the case of, initially when we write our chemical reaction, we start out with one of each. And then we're going to multiply it by a factor, these coefficients. We are not going to change the subscript, though. The subscript is telling us how many atoms are in that molecule. And if I was to change the subscript, then I change the actual molecule I started with. We're not changing the molecules, we're just changing how many we have of them. And so that will be out front. Then as you start to balance each of the elements, you want to try to change the coefficients in such a way that all of them end up balanced on both sides. So how I would do it is I would list out the chemical elements. So I have carbon, hydrogen, and oxygen as my atoms, and I have reactants, and I have products. So if we look at how it starts out, initially I have 1 carbon on the reactants and 1 carbon on the product. 4 hydrogens to start out with on my reactants. And initially I only had 2 in my products. Then oxygens, I had 2 oxygen atoms in my reactant, and I have 1, 2, 3. So 2 here and 1 here for my product. So I have 3 total here. So we can see our carbons look balanced already. So we won't start there. I would want to start with my hydrogens. So I have 4 in my reactant and 2 in my product. So that's where we add our 2 out front, in front of water. Now that changes our hydrogens to 4, but it also changes our oxygen. Now I have 2 oxygens from my CO2 here, and I have 1 times 2. So that's going to end up giving me 4 oxygens in my product. So my hydrogens are balanced. My oxygens, I need twice as much in my reactant. So that's where the 2 out front of O2 comes. That changes my oxygen amount to 4. And so now oxygen is balanced and carbon is already balanced. So again, we just start with one element, ideally one that only shows up once on each side, and work our way through until we kind of find this balance. There are a few different types of chemical reactions. The first type that we'll label is called a combination reaction. This is where we have 2 or more reactants that combine into one single product. Lots of different types of reactions do this, but basically if we have 2 types of elements coming into one, then that is our combination reaction. So in our case here we have magnesium metal and oxygen, the molecule, coming together to form ionic magnesium oxide. So we would call that or classify that as a combination. Next type is decomposition. This is basically the opposite of combination. We can also sometimes call it combination synthesis. Decomposition is when we have one reactant breaking up into 2 or more products. Oftentimes this happens when these elements are heated. Combustion reactions are a reaction that involve oxygen from the air generally as reactant. Oftentimes these reactions involve hydrocarbons as a reactant. So these are molecules that have carbon and hydrogen in them, and sometimes even oxygen. And so these hydrocarbons react with O2. Oxygen is always a reactant in a combustion reaction. And then oxygen basically attaches to each of those hydrocarbons. So we get carbon dioxide and water if a hydrocarbon is our other reactant. This will always be the case that we have carbon dioxide and water. And so we can then balance it. Again, since we saw like with the other example, we won't ever start with balancing oxygen atoms. We'll start with carbon and hydrogen, and oxygen will be our last step. So we are familiar with combustion in our daily lives because that is what occurs when we burn different substances, wood in a fire, or just like methane or propane when you go camping, or butane. So these are combustion reactions. There are a few different ways to write balanced equations. What we've shown so far is a complete molecular reaction. This is where everybody who's a part of a reaction gets shown. So here I have, silver nitrate and potassium chloride forming silver chloride, a solid, and potassium nitrate, an aqueous. So I have aqueous phase, solid, and aqueous. So the big thing that happened, if we were to look at those details, is that we formed a solid. The next thing we can do is break the substances up into their complete ionic equation. This is where anything that is aqueous will get broken up into the ion. So I have silver aqueous, nitrate aqueous, potassium aqueous, and chloride aqueous. Because when we have something that's aqueous, it is dissolved in water. So when we have these ions, when they're dissolved in water, they actually break apart and the water will surround them. So since these are both aqueous, they all split up into their ions. Now when something is in the solid or liquid form, or gas technically, they stay together. So the ionic substance didn't break apart, right? That's why it's a solid. So then we would separate the other aqueous ionic compounds, and this is our complete ionic, just showing all of the ions separated on their own. To get the net ionic, what we want to do is we remove spectator ions. These are the ions that didn't do anything. They started aqueous in the reactants, they end aqueous in the product, and they're not really doing a whole lot. They are not really involved. They're basically just watching. So here, if we look at our complete ionic reaction, potassium and nitrate stayed aqueous. So I can actually find them on the other side, potassium and nitrate. If we cross them out, we get our net ionic, which is who is left over. That is our sodium and our chloride ions producing our solid sodium chloride later. Not sodium, sorry, silver. So being able to go in between our molecular reaction up here, molecular equation, to the net ionic is going to be an important skill that you're going to start to build. And then down here, these are solubility rules. These are basically telling us who's going to dissolve in water always, who's always going to form a solid precipitate, and who can kind of do both, depending on what they're with. We'll start to learn and focus more on that when we do our solution chapter. But if you can remember that the alkali metals are always going to be aqueous every single time. They're never going to form a solid, as well as ammonium. That would be a really great thing to start with. So remembering that alkali metals and ammonium, as well as, we'll just stay with that. As well as nitrate. These will always, always, always be aqueous when you find them in a solution. So I'm going to write a little star here because I want you to start to think about alkali metals and nitrate. Now we're going to talk about more of like the math part of this chapter. So we talked about balancing the equations. Now we're going to start to deal with some calculations. So the first thing you want to be able to do is find the molecular weight or the molar mass of a molecule. So what you do is, if we had something like water, H2O, to find out how heavy that is we take the mass of the hydrogens plus the mass of the oxygen to get our total. So I have 2 hydrogens, and if we look on the periodic table, they weigh about 1.01 grams per mole. That's our molar mass. And then I have an oxygen, I just have one of them, and they each weigh 16.00 grams per mole. So the molar mass of water is going to end up being 18.02 grams per mole. So we're just finding out on the periodic table how much each of these elements weighs, and then we'll add them up for the total. To find out the percent composition, this is basically how much of a compound is made up of a given element. So percent of the element, just like if I wanted to know what percent of the class lives in Salt Lake City versus somewhere else, I would add up all of the students who live in Salt Lake City, divide by the total number of students, and multiply by 100. I'm going to do the same thing here. I'm going to add up all of the number of atoms of that element. So we'll just call it number of atoms of X. I'm going to multiply that by the molecular weight of X. And then I'm going to divide it by the molecular weight of the whole compound times by 100 to make it a percent. So for water up there, I could, if I wanted to find out the percent of hydrogen, I have 2 hydrogen atoms, multiply by the molar mass of hydrogen, 1.01 grams per mole, divide by the molar mass of water, so 18.02 grams per mole, and then times by 100. So that would be kind of the process of finding out how much of water is made up of hydrogen. Molar mass and molecular weight are synonymous. Oftentimes molecular weight is in a unit called AMUs, or atomic mass units. But just knowing that actually AMU and molar mass, those units are synonymous and they can be interchanged. So if I found out that the molecular weight of water is 18.02 AMUs, it's also 18.02 grams per mole. And since grams per mole has 2 units in it, right, grams and moles, we actually get to use these as a conversion factor later when we want to go from some substance in grams into the mole unit. The next number we're going to learn about is called Avogadro's number. And the nice thing about this is it's nothing that it doesn't differ by the substance like molar mass does. It's always the same number. And it is 6.02 times 10 to the positive 23. And that's how many particles there are in 1 mole. So we can think of Avogadro's number as like a baker's dozen in chemistry. So we know that a dozen, if I have 1 dozen eggs, then that means I have 12 eggs. If I have 1 mole of eggs, then that means I have 6.02 times 10 to the 23rd eggs. Obviously, we're not going to be dealing with eggs in the sake of chemistry, but we are going to talk about atoms and molecules. So it's a grouping of things. So we're going to use both Avogadro's number and molar mass to go between moles. So moles is kind of our central unit. If I want to go in and out of moles to grams, I'm going to use molar mass. If I want to go between moles and how many atoms or molecules I'll have, I'll use Avogadro's number. And I will just give you a little heads up that molar mass is going to be way more common of a conversion than Avogadro's number. Only when I ask for how many atoms or molecules are in a sample will we use Avogadro's number, and oftentimes it's not as important as how much something might weigh. So you might be wondering, why do we need to be in moles? Why can't we just be in grams? So moles is a more relevant term that's related to an amount. So when we write our reactions, like if before I had 2 hydrogens plus 1 oxygen molecule went to, let's do this colorful, it went to 2 waters, right, like that. Since my conversion between molecules, so if I wanted to go from molecules to moles, it always is using Avogadro's number, or N sub A. Okay, this is a constant. So we could, if we're working with molecules, so how many, right, I have 2 hydrogen atoms for every 2 water, or 1 oxygen molecule for every 2 water molecules. I could use that. I can think of it in terms of how many molecules I have, but I could also do that in a grouping, how many moles I have. And since when we weigh things on a scale in the lab, we're in grams. Now, every molecule weighs a different amount. So if I had 5 grams of water versus 5 grams of hydrogen versus 5 grams of oxygen, my moles are going to be quite different from that. So equal mass does not mean equal amount, but equal amount of moles does mean the same amount. So we want to be able to get to moles so that if I want to find out how many, if I have a certain amount of reactant, I want to maybe be able to predict how much product I could make. So we're going to use the chemical reaction, the coefficients, to do that. So how we're going to do that? Let's say I had a sample and I had 3 moles of H2 and I had 7 moles of O2. Maybe I want to find out how much hydrogen I can make from each of these. So let's say I have 3 moles of H2, and I know that 2H2 plus 1 O2, I'm just going to call it O2, goes to 2 waters. So if I want to find out how much water I can make from my 3 moles of H2, then I get to use the chemical reaction. So this is where I'm using my balanced chemical reaction, we also call it a molar ratio, to go from moles of H2 to moles of water. So I'm going to write moles of H2 on the bottom and moles of water up top. This is what I'm trying to find. I go to my chemical reaction and I can find my number in front of H2 is 2. My number in front of water is 2. So that's what I'm going to put in here. So if I started with 3 moles of hydrogen, then I'm going to technically make 3 moles of water. If I start off with 7 moles of oxygen, right, here we go, up here, let's find out how much water I could make just from that. So again, I'm starting off with oxygen, so I'm going to use my units to go down bottom. Moles of oxygen. I want to find out how much water I can make. I'm going to go to moles of water. Again, I'll go to my chemical reaction. Here I have 1 oxygen for every 2 waters. So I'll put a 1 in front of oxygen, a 2 in front of water. So in this case, I could make 14 moles of water. So if I think about who I'm starting with, I know that oxygen is going to be able to make more waters in this case with this sample that I had than my hydrogen would be able to. Here's another way to kind of look at how you can go between grams of molecules or atoms to moles is kind of our middle unit. And then if I wanted to go to molecules, I can adjust with Avogadro's number. Earlier we learned about, in the past chapter, empirical formulas. Remember, empirical formulas are the formula that has the lowest whole number amount of each element. So how this actually gets determined, this can get determined in lab, is they send in a sample for analysis. And it might say that I came back with 11.11% hydrogen and 88.89% oxygen. Okay, so what is the sample, I wonder? So what you do to find out the empirical formula, first thing is you take the percent masses that you get and you assume you have a 100-gram sample, which means that basically if I had 11.11% hydrogen, then I really had 11.11 grams of hydrogen and 88.89 grams of oxygen. So first step, easy. Turn all of those percentages into grams. Next step is you're going to convert your grams of every element into moles. So you're going to take the molar mass of each element and take your mass divided by the molar mass. So I want to get into from grams to moles for each of these. So the molar mass of hydrogen is 1.01 grams. The molar mass of oxygen is 16.00 grams per mole. So we're going to calculate that. So for hydrogen here, we get exactly 11 moles of hydrogen. And for water, we get 5.55 moles of oxygen. And now, so the next step, now that we have the moles of each, is we find the ratio. So what you want to do here is divide by the smallest number. So we look at our 2 moles, and divide by the smallest number. Looks like oxygen has 5.5 and hydrogen is 11. So we're going to divide each number by 5.5. And so what we get here is 2 hydrogens and 1 oxygen. So this tells us our ratio of each one. So that means I have H with 2 of them and 1 oxygen. So our sample from our original analysis is water. So you take that number and make them subscripts. In the case that when you take the ratio, you get a number like, let's say I had 2.5 of X and I had 1 of Y, then what I would want to do is multiply by a number that would give us the first whole number. So for a half, I would multiply each of these by 2. So meaning I'd have X 5 and Y subscript 2. And that would give me my whole number. All right, so that's how to determine empirical formulas. I'm not going to have you worry about combustion analysis. It's basically the exact same thing, but a little bit more complicated, and you don't need to worry about it. So now we're going to talk about limiting reactants. This is basically the reactant that is going to run out the quickest. So the thing that you have the least of. So the one that shows up in the smallest stoichiometric amount or molar amount. So who are you going to run out of? So if I look at the reaction here where I have 10 hydrogens and 7 oxygens, we know that we have 2H2 plus 1 O2 goes to 2 waters. We saw that earlier. What we get to do is find out how many waters each of our reactants can possibly make. And the goal is to find out who will make the smallest amount of waters. And I'll be general here, so the smallest amount of product. You always pick a product and find out who will make the smallest amount. So we're going to assume instead of 10 waters, we have 10 moles of water. And keep in mind that moles and number of molecules is going to be equivalent because of Avogadro's number being a constant. So I have 10 moles of H2 and I have 7 moles of O2. So we're going to find out who's going to make the smallest amount of moles of water. So moles of water. Moles of water. All right, so what I'll do is now I'm going to use my chemical reaction. We don't even need to look at our sample anymore. We're just going to look at our chemical reaction. So both cases, I want to find out how many moles of water I'm going to make. So the top will be the same. Sticking with hydrogen first, we know that from our chemical reaction, we have 2 hydrogens for every 2 waters. So I'll do 2 moles of hydrogen for every 2 moles of water. So once we do this calculation, we can see 10 times 2 divided by 2 will give us 10 moles of water. If I do the same thing now for oxygen, looking at my chemical equation, I have 1 oxygen for every 2 moles of water. So I'll put 1 mole of oxygen for every 2 moles of water, and I get 14. So we go look and see who is going to run out first. Who makes the smallest amount of product? Well, it looks like 10 moles is our smallest, so that means hydrogen here is going to run out first. It's only going to make 10. Could have made some more with oxygen, but we don't have enough hydrogen. So we would say that hydrogen is our limiting reactant. And we can see that here in our picture example, we still have 2 molecules of oxygen left over, and all of our hydrogen got used. So that gets into what theoretical yield is. Theoretical yield is the maximum amount of a product that can be made. So this is theoretical. This is based off your calculation. So before, our theoretical yield was based off our limiting reactant. That was our 10 moles of water that could be made. The actual yield is what after you do the lab, how much did you make of your product? So how much water did I make? So percent yield is very similar to percent and other things. Percent yield is going to be the actual yield from experiment divided by theoretical yield. This is from your limiting reactant calculation. And then you're going to times by 100. So let's say in the lab, we did this example, we did this water creation from hydrogen and oxygen, and in the lab I made, let's say the actual yield was 5.5 moles of water. So what I would do to find percent yield would be my actual yield, 5.5 moles of water, divide by my theoretical yield, which was 10 moles of water, times by 100, and we get 55% yield. All right, so this is just a lot of practice we're going to be working on together. So come with your questions to class so I can help you.